For decades, NASA collected massive amounts of data from space missions, far more information than scientists could fully process or deeply analyze at the time. Most of that data was carefully stored, labeled, and archived, not because it was useless, but because technology and time were limited back then. Those old datasets did not disappear or lose value. They simply waited quietly while science moved forward in other directions. Recently, scientists started reanalyzing old NASA data, not searching for surprises, but using modern computers and better models. What they noticed was not dramatic or cinematic, but subtle enough to be disturbing in a scientific way. There were small inconsistencies, weak patterns, and strange measurements that never fully matched expectations. Decades ago, these details were easy to dismiss as instrument noise, calibration limits, or simple measurement error. That decision made sense at the time because space missions were expensive and focused on answering bigger questions. But when the same data is viewed today, those ignored details no longer feel random or meaningless. They appear repeatedly across different missions, instruments, and regions of space. These were not mistakes large enough to trigger alarms, but they were consistent enough to deserve attention. NASA missions like Voyager, Pioneer, and early probes gathered information from environments we still barely understand today. They measured radiation, magnetic fields, particle behavior, and background signals far beyond Earth's influence. Most public attention went to major discoveries, while smaller, unexplained results were archived and forgotten. Science often works that way because progress focuses on clear answers, not inconvenient questions. But time changes how we understand information, especially when new data adds context to old results. What once looked like meaningless noise can later reveal structure and pattern. What once seemed irrelevant can become important when combined with decades of additional knowledge. The data itself never changed. Only our ability to understand it did. This is not a story about secrets, cover-ups, or hidden messages buried by NASA. It is a story about limits, assumptions, and how science sometimes moves past things it does not yet understand. When old data begins to challenge modern expectations, it forces uncomfortable questions. Were we wrong to ignore it? Or were we simply not ready to see what it was showing us? Because sometimes, the most important discoveries are not new signals from space. They are old signals we finally learned how to read. To understand why this data was ignored for so long, it is important to understand how real science works under pressure, limited budgets, and strict mission goals. Space missions are built to answer very specific questions, and any data that does not help achieve those goals is often treated as secondary or irrelevant. When early probes like Voyager and Pioneer sent information back to Earth, scientists focused on keeping the missions alive and successful. If strange data did not threaten the mission or clearly point to a discovery, it was rarely given long-term attention. There is also a psychological factor that scientists openly admit today, even though it feels uncomfortable to discuss. When data does not match existing models, the first assumption is almost always error rather than discovery. This is not incompetence, but a defense mechanism, because chasing every anomaly can destroy time, funding, and careers. As a result, many unusual measurements were labeled as instrument noise, calibration drift, or environmental interference. Those labels did not mean the data was understood, only that no better explanation existed at the time. One well-known example involves deep space probes that experience tiny but consistent changes in speed far from Earth. For years, these changes were explained away as heat radiation or engineering effects without deep investigation. Only decades later did scientists seriously revisit the data and realize the explanation was far less certain than assumed. Another overlooked mystery involves background radiation measurements that change slightly depending on location in space. The differences were too small to cause alarm, but too consistent to fully ignore once modern analysis tools were applied. At the time, there was no framework to connect these details into a larger scientific question. Scientists also believed future missions would collect better data and make old problems irrelevant. But many early probes traveled farther than anything launched since, making their data unique and impossible to replace. Once those missions ended, attention moved forward toward new projects instead of backward toward unresolved questions. Science rewards new discoveries more than re-examining old uncertainties, even when old data still holds value. This creates blind spots where anomalies remain unstudied, not because they are meaningless, but because they lack ownership. Some data falls between disciplines, not fully belonging to physics, astronomy, or engineering, making responsibility unclear. What changed recently is not curiosity, but capability. Because modern computing allows comparisons across decades of data. When datasets are combined, patterns begin to appear that were invisible when each mission was studied alone. Once patterns emerge, ignoring them becomes far more difficult, even if the explanation remains unclear. This is the moment where old data stops being history and starts becoming a question again. The information was always there, quietly waiting. We simply did not have the tools or perspective to understand it yet. One of the most famous examples hidden in old NASA data is something scientists once called the Pioneer anomaly. And for years, nobody knew what to do with it. The Pioneer spacecraft were slowly drifting off course in deep space, not enough to cause failure, but enough to quietly break predictions. At first, this tiny deviation was ignored because it seemed too small to matter and easy to blame on engineering limitations. But the strange part was consistency, because the slowdown appeared again and again in data collected far from Earth. For decades, this anomaly sat in archives, mentioned briefly in papers but never treated as a serious scientific problem. Only much later did researchers return to the data with better models and realize the explanation was not as simple as first assumed. Another overlooked mystery appears in old radiation and particle measurements taken far beyond Earth's magnetic influence. Some probes detected unexpected variations in background particle behavior that did not match predictions from existing models. At the time, scientists assumed the instruments were affected by unknown local conditions or technical imperfections. Those assumptions were reasonable, because no clear theory existed to explain what was being observed. But when modern scientists compared data from multiple missions, similarities began to appear across different regions of space. Patterns that once looked isolated started to feel connected, even though the meaning remained unclear. Voyager spacecraft also recorded changes in particle density and magnetic behavior as they moved toward interstellar space. These transitions were not sharp or dramatic, but gradual, making them easy to dismiss as noise rather than structure. Today, those same transitions are being re-examined as possible signs of boundaries we do not fully understand. There are also strange timing irregularities found in early deep space signal transmissions. Signals sometimes arrived slightly earlier or later than expected, beyond what simple models predicted. Engineers adjusted systems and moved on, assuming minor errors rather than deeper implications. At the time, nobody imagined these timing shifts could relate to large-scale properties of space itself. Another rarely discussed issue involves unexplained fluctuations in cosmic background measurements. The differences were subtle, but persistent enough that they appeared across different missions and instruments. They did not point to a single discovery, so they were quietly archived and forgotten. Science prefers clear answers, not collections of uncomfortable questions. What makes these anomalies interesting today is not that they prove something extraordinary. It is that they survived multiple missions, multiple instruments, and multiple explanations without fully disappearing. That persistence is what makes scientists uneasy now. Because random noise usually fades when you look closer. But structure tends to remain. And when old data refuses to disappear, it stops being history and starts becoming a problem. One of the most uncomfortable things old NASA data revealed is not a single mystery, but the possibility that our models of space were always incomplete. Scientists prefer problems that can be isolated, tested, and solved. But some anomalies refuse to fit into any single category or explanation. Instead of pointing to one strange object or event, the data hinted that something about space itself might behave differently than expected. That idea is far more dangerous to science than a mystery signal, because it challenges the foundation, not just one conclusion. For many years, space models assumed that conditions would become more uniform the farther probes traveled from Earth. Small fluctuations were expected, but long-term irregularities across huge distances were not part of the standard picture. Yet some probes kept reporting variations that never fully disappeared, even after accounting for known physical effects. At the time, these differences were dismissed as acceptable imperfections rather than meaningful clues. Another issue involved early computer simulations that scientists relied on heavily to interpret mission data. Limited computing power forced researchers to simplify complex systems, smoothing out details that seemed unimportant. Those simplified models worked well enough to plan missions, so few people questioned what they left out. But when old data is compared with modern simulations, those missing details suddenly matter much more. Measurements that once looked fine now sit slightly outside expected ranges in ways that feel uncomfortable rather than random. Not enough to claim a discovery, but enough to quietly weaken confidence in old assumptions. There is also a pattern that only appears when data from many missions is combined instead of studied separately. One probe alone looks unreliable, but several probes showing similar behavior across space is much harder to ignore. Decades ago, comparing data sets like that was almost impossible due to incompatible formats and limited storage. Today, those barriers are gone, and the comparisons raise questions that never had a chance to be asked before. Another rarely discussed factor is professional caution, which protects science but also slows uncomfortable conversations. Scientists are trained to avoid bold claims without clear explanations, because being wrong has serious consequences. So, when data behaves strangely without offering answers, silence often feels safer than speculation. That silence does not mean nothing was found, only that no explanation felt strong enough to defend publicly. And that is why these old data sets suddenly matter again. Because ignoring them is no longer safer than admitting we may have missed something important. The most unsettling idea is not that old NASA data contains errors, but that these small anomalies might be related to each other in ways we never tested. For decades, scientists studied space missions separately, assuming each anomaly belonged only to its own mission or instrument. That made sense at the time because combining data across missions was technically difficult and often unreliable. But when modern researchers started comparing data sets across decades, patterns began to quietly appear. Not clear answers, but similarities in behavior that repeated far more often than random chance would suggest. Some anomalies showed up at similar distances from the Sun, even when missions used different instruments and trajectories. Others appeared only in deep space, far from Earth's magnetic influence, where models were supposed to be simpler. Instead of clarity, space seemed to behave in layered ways that did not match clean textbook predictions. Another surprising detail is that many of these anomalies were not dramatic spikes or sudden events. They were slow, gradual shifts that unfolded over long periods of time, making them easy to ignore. Humans are naturally drawn to sudden changes not quiet trends that only reveal themselves years later. That bias may have shaped what scientists noticed and what they filtered out as unimportant background behavior. Some researchers now suspect that space is not as empty or passive as once assumed. Not alive, not intelligent, but structured in ways we still struggle to model correctly. This does not mean physics is wrong, but that it may be incomplete in regions we rarely observe directly. Old missions accidentally collected data from those regions, even though they were not designed to study them. That makes their measurements messy, indirect, and hard to interpret, but also extremely valuable. Another uncomfortable possibility is that these anomalies reflect transitions between different space environments. Boundaries that are not sharp, not visible, but still physically meaningful. Voyagers crossing into interstellar space hinted at this, but even that event raised more questions than answers. If space contains layers, gradients, or long-range effects we barely understand, then old data becomes critical. Because new missions are expensive, rare, and often designed with existing assumptions in mind. Old data offers something different. It captures moments before assumptions hardened into rules. That is why scientists are returning to it now, not out of desperation, but curiosity. Because if these anomalies are connected, then we did not just miss a detail. We missed part of the map. At this point, many people expect the story to turn toward aliens, secret signals, or hidden intelligence. But that is not where the real problem is. The most important part is that these anomalies do not point to life, but to gaps in how we understand space itself. That may sound less exciting, but it is actually far more serious for science and future missions. If space behaves differently than our models predict, then every long-term mission depends on incomplete assumptions. Navigation, communication, radiation protection, and energy planning all rely on models built from past understanding. When those models quietly fail at the edges, missions become riskier without anyone realizing it in advance. Another uncomfortable fact is that modern missions are often designed to confirm existing theories, not challenge them. That makes science efficient, but it also makes it conservative, especially when budgets and public trust are involved. Old missions were messier, less optimized, and more experimental, which allowed them to stumble into unexpected data. That accidental nature is why their anomalies feel so important today. They were not filtered by expectations as strongly as modern missions often are. This creates a strange situation where older, imperfect data may be more honest than newer, cleaner measurements. Not because it is better, but because it captured reality without knowing what it was supposed to see. Another key point is that science advances by tightening explanations, not expanding mystery forever. Eventually, these anomalies will likely receive explanations rooted in known physics or new refinements. But the delay itself matters, because it shows how easy it is to overlook slow, quiet inconsistencies. These are not discoveries that arrive with headlines or celebrations. They arrive as doubts that slowly spread across models and assumptions. For the viewer, this matters because space exploration is entering a new phase. Humans plan longer missions, deeper probes, and permanent presence beyond Earth. Those plans depend on understanding space not as empty background, but as an active environment. If old data was warning us about that, then ignoring it was not harmless. It was simply invisible until now. And the fact that it took decades to notice should make us pause. Not because science failed, but because it works slowly and cautiously by design. Sometimes too slowly for the questions we are now asking. Here is where old NASA data stops being a historical curiosity and starts affecting decisions being made right now about humanity's future in space. Plans to return to the moon, build long-term stations, and send humans to Mars all rely on models created from our current understanding of space. Those models assume space behaves in predictable, stable ways once you move far enough from Earth. But old data suggests that assumption may be too simple and, in some cases, quietly wrong. Radiation levels, particle behavior, and magnetic environments may change more gradually and unevenly than expected. That matters because long-term exposure is one of the biggest dangers for human space travel. Even small miscalculations can compound over months or years, turning manageable risks into serious problems. Old probes detected radiation patterns that did not fully match forecasts, but were ignored because missions were short. Human missions will not be short. They will last months, years, and possibly entire lifetimes. Another issue involves navigation and communication over extreme distances. Tiny timing inconsistencies in old signal data were once dismissed as technical noise. But over interplanetary distances, tiny errors can grow into major deviations. Modern missions correct for this with redundancy, but redundancy depends on knowing what to expect. If space behaves slightly differently in deep regions, corrections may lag behind reality. There is also the question of infrastructure. Future plans involve satellites, relays, and habitats that assume stable conditions. Old data hints that space environments may shift subtly over time, not violently, but persistently. That kind of change is harder to design against than sudden events. It does not trigger alarms. It quietly erodes margins. Perhaps the most unsettling part is that many of these warnings came from missions that were never meant to study these effects. They were accidental observers, passing through regions modern missions may avoid or simplify. That makes their data uniquely valuable and deeply inconvenient, because it does not fit neatly into mission planning documents or funding proposals. Yet ignoring it now would be a choice, not a limitation. This is why scientists are returning to old data sets with urgency rather than nostalgia, not because they expect dramatic discoveries, but because the future depends on understanding what we already passed through without fully noticing. The universe may not be hiding secrets from us. It may have already shown us the risks, quietly, long before we were ready to listen. There is an uncomfortable truth in modern science that rarely gets attention, because it sounds backward and challenges the idea that progress always comes from something new. New discoveries attract headlines, funding, and excitement, while old data is treated as finished, outdated, and already understood by previous generations. But old NASA data has one critical advantage that modern missions do not, because it was collected before today's assumptions hardened into rules. Early space probes were not optimized to confirm existing theories, because many of those theories did not exist yet at the time. They measured whatever they encountered, often without knowing what was important, creating messy but honest records of space conditions. That messiness is usually seen as a weakness, but it also means the data was not filtered by expectations or corrected to fit models. Modern missions are efficient, precise, and targeted, but they are also narrow, designed to look for specific outcomes. Anything that does not match predictions is often averaged out, deprioritized, or labeled as secondary background information. Old data did not have that filter because scientists did not yet know what the correct answers were supposed to be. This means early missions sometimes captured behavior in space that modern missions may unintentionally ignore or smooth over. Another rarely discussed detail is that many old probes traveled farther and longer than most missions flying today. Some of them reached regions of space that are difficult or politically impossible to revisit with current budgets and priorities. That makes their measurements irreplaceable, even if they are imperfect and difficult to analyze. When scientists re-examine this data today, they are not hunting for dramatic discoveries or shocking revelations. They are looking for consistency, repetition, and patterns that survive decades without clear explanations. Random noise usually disappears when technology improves and analysis becomes more precise. But real structure tends to remain, even when tools and models change. If something in space behaved strangely then and still looks strange now, the problem is not error. The problem is understanding what we are actually looking at. That is why old NASA data has become so important again. Not because it contains hidden answers, but because it contains unanswered questions we finally have the tools to face. For decades, humanity prepared for space as if it were an empty and predictable stage, believing the main challenge was technology and distance rather than understanding the environment itself. Rockets, habitats, and missions were designed using simplified models that treated space as stable once basic physical laws were measured near Earth. Old NASA data quietly suggests this confidence may have been premature, not because space is hostile, but because it behaves in more complex and uneven ways than expected. Instead of a static background, space appears to be an active environment with layers, gradients, and slow changes that do not announce themselves through dramatic events. That kind of complexity is more dangerous than sudden disasters, because it does not trigger alarms and instead erodes safety margins gradually over long periods. Human missions to the Moon, Mars, and beyond rely on predictions that work in short missions, but may quietly fail during years of continuous exposure. Old probes pass through these conditions briefly, while future astronauts will live inside them for months or even entire lifetimes. Radiation exposure, navigation drift, communication delays, and environmental variability may compound slowly in ways never fully tested before. Old data did not predict catastrophe, but it hinted that long-term stability might be harder to maintain than planners assumed. The most unsettling realization is that space did not suddenly become more dangerous as we learned more about it. Humanity simply began planning permanent presence before fully understanding the environment it was already moving through. NASA never hid these details, because they were never secrets, only measurements that did not fit neatly into mission goals. Those measurements waited quietly in charts and data sets until technology and perspective finally caught up. Now those questions can no longer be ignored, because humanity is no longer just visiting space for short experiments. We are preparing to stay for long durations, build infrastructure, and depend on space behaving the way we expect. Staying requires understanding not only how to arrive safely, but what we have been passing through all along. The universe may not be hiding anything from us, because it never needed to communicate in the first place. It may have already shown us what matters through data we were not ready to interpret at the time. That realization does not end the story of exploration, but it changes how carefully the next chapter must be written.